very warm welcome. My name is Verena Albrecht. I'm the project manager here at Nürnberg Messe for PARTEC, one of the leading international science congresses for particle technology. In 2025, PARTEC will again take place in co-location to PARTEC Technofarm from 23 to 25 September here in Nürnberg at the Exhibition Center. The motto of PARTEC 2025 is Particles Empowering Tomorrow, Innovations for Our Global World. And we're expecting about 550 participants, scientists, engineers, doctoral students, and international experts in particle technology. So PARTEC and PARTEC Technofarm bring together what has always belonged together, science and industry, hand in hand for progress. And it is therefore fitting that all PARTEC participants also have free access to PARTEC Technofarm, our international trade fair for process operations. A very special thanks today go to our honorary sponsor, the VDI Society Chemical and Process Engineering, with whom we have enjoyed decades of successful cooperation within the framework of PARTEC Technofarm and PARTEC. And yes, we are very pleased that Daniel Schröder from VDI is joining us today.
Thank you, Verena. Hello, everyone. And on behalf of the VDI, a very warm welcome to you all. My name is Daniel Schröder, and I'm a research associate at the VDI. As the conceptual sponsor of the Congress, we are delighted to contribute to the development of the program. And at this point, I would also like to encourage all potential speakers who have not yet submitted an abstract to do so. The submission deadline is January the 10th in 2025. Now I'd like to hand over directly to our two speakers. We start with Professor Lutz Mädler. He's director of the Leibniz Institute for Materials Engineering, IWT in Bremen, and he's also the chair of the PARTEC 2025. The title of his presentation is From Exploding Droplets to Nanoparticles for Catalysts, Sensors and Batteries. And the second speaker is Professor Nikolaus Vogel, Institute of Particle Technology, Department of Chemical and Biological Engineering, Friedrich-Alexander-Universität Erlangen-Nürnberg. He talks about supraparticles, powders with emergent functionalities. Okay, let's start. Professor Mädler, the stage is yours.
Thank you very much, Daniel. It's my pleasure. So welcome all, and I hope I see you not only today, but also on the PARTEC 2025. I will share my screen. Let me just get this ready. So, all right, so you should see my screen. I'm very happy to present this topic here for me today, from exploding droplets to nanoparticles for catalyst sensors and batteries. And today I want to actually stick a little bit to batteries and tell you how we make battery materials and why we think it's important to be careful with doing that in the processing. And to start with this, I think that we need energy storage materials is clear. And what I want to present to you here is the anode materials. It's lithium titanate based lithium battery. And I will look a little bit at the performance, but also at the costs, and also at how we're going to use the resources to make them. And how we make our materials here in Bremen and is by a process called spray flame pyrolysis. And this is a picture, it's the latest picture, is from a PhD thesis that was just finished this year by Malte. And Malte made this very nice picture, and it shows how we actually get from a precursor solution, and this will be a lot, emphasis will be on this precursor solution down here, up to the nanoparticles up here. Let me see if I can actually have a pointer here. Okay, so we go from this liquid to these nanoparticles, and we use these kinds of reactors here. And these reactors are so-called spray flame reactors. So it's a spray where you have liquid, this kind of liquid, and you disperse that with some dispersion gas. Most of the time it's oxygen, and you disperse that into very fine droplets. And these fine droplets you ignite with what we call a supporting or pilot flame. Here is methane oxygen. It can also be hydrogen oxygen. And that provides the heat to ignite these droplets. And these droplets, they burn on their own. So basically this liquid here is combustible. And then you have a co-flow. And while these droplets are evaporating, you set free some of the metals you have dissolved in that solution here. And while you set them free, you have them in the gas phase as individual molecules in the best case. And then these individual molecules, they nucleate and create your new materials. And then they coagulate to form bigger particles, they sinter. And at some point, you can quench this flame, basically because of the fuel is being burned out. And you have a lot of gas entrainment in this gas flow. And then you cool this process down very quickly. And then you quench these particles in the state of nano. So they're really small particles. And they're good for batteries and for other applications, catalysts, sensors, and so on, because they have a high surface area and they have very specific composition and they are very crystalline. So this process is very nice, but it's also complicated, and I'll show you that in a second. And it involves different aspects: the precursor solution, the atomization, the evaporation, and the particle formation. And it's different lengths and time scales we're dealing with. But today I want to focus a little bit more on this solution here. And as I said, we make, as an example, lithium titanate. And this lithium titanate consists of lithium and titanium. And so in that solution I just showed you, you need a source of titanium and you need a source of lithium. And now it's a question what you put in there. And then you need some kind of solvent. And again, remember, that solvent should be combustible. So all the energy, or most of the energy in that process that drives the process, comes from the liquid itself. So the task here is to put some of those metal into a combustible liquid. And what we do is we use nitrates, but most of the time also we use metal organics, and we try to mix them together. And that's not always very successful. As you can see here, these are the solvents: ethanol, benzyl alcohol, tetrahydrofuran, xylene, ethioxonic acid. So these two here are one of our favorites because they have good combustion enthalpy, but they are not always dissolving some of these precursors. So these are the precursors here: lithium nitride, lithium tetrodoxide, lithium acetonate, and TTIP, the titanium precursor. So only the green ones you can actually use, and then you leave them. Basically, you can dissolve them, but then you have to also dissolve them together. So basically, it's not enough to have one metal in there, but we have two metals and they should be stable, not reacting before you actually go into process. And this is shown here. So some of them we have to exclude just because they react already before. And once you have that solution, you just need that reactor, burn everything, collect the particles, and look on what you get. And this is what you get. This is, of course, our best case here. That's why I'm showing it. And this is really lithium titanate. And it's very phase pure. I show that in a second to you. You can see that here on this XRD pattern. It matches the lithium titanium perfectly. We did some lead fed refinement to find that. And we can also confirm that on some high resolution TEM, where we actually can take that crystal structure from the XRD and check if we really have those crystals also in the TEM. And as you also see, our particles are very crystalline, which is good for many, many applications. And but this is not the case for all those precursor solutions. And that's exactly my point. So what I just showed you was this combination here with 100%. So we only get a few of them that have 100% phase purity, and some others are not really getting 100% phase purity. In some cases, you only get 70% or 60 or even 0% of phase purity of that mixed metal oxide, lithium titanate. And the question is, why is that? And this is what my talk is about today. And this is again Malte here, who just finished his PhD. And that's a very simple spray flame, simple in terms of there's no metal inside. So it's just ethanol burning as a spray flame, and it looks very nice. And if you put some of these metals, in this case, it's an iron precursor, but doesn't matter. It's a similar story. The flame changes, right? Of course, flame color changes because these metals, they have their own spectra that they emit once they're excited. But if you look with the flame sheet into these flames, you can actually see the droplets. Okay, there's a very thin sheet, and then you see in that thin sheet, you can see the droplets of that flame. And if you put the metal inside, things look completely different. Okay, so what you see here is some droplets that go like, it looks like they are fireworking, and then you have this fume, this, yeah, it's kind of a mist fume, and these are actually the nanoparticles. The very small nanoparticles, they basically scatter the light here. And the question is, what is really different? You see a real difference, and the difference is you just put that metal. So the metal inside makes a huge difference, and that's why my group has set on this journey on really looking at the individual droplets and what they are doing and how this whole reaction and getting into gas phase happens. And we do that with what we call single droplet combustion experiments. We call these experiments generic experiments. And so we basically have those nanoparticles here, and we those droplets here, and then we let them fly. We ignite them we have those droplets here. We go up, down. We have those droplets here. We ignite them here. We let them burn, and at some point they react. And in most of the cases, they form a micro explosion. And you can see that here. So this is 200 microns. These droplets are below 100 microns. They fly, and at some point they get into micro explosions. But some of them, they have actually residuals. And that means that they do not really explode well. And the question is, does it matter or does it not matter? And I have a sequence right here, and it actually does matter. While droplets that are not like this, completely reacting, to see some of them, but then there's something left, right? Also here, down here is something left. They are not completely reacting. They don't form this really mixed metal oxide, this atomically mixed metal oxide. And that's why we really wanted to look even closer into it. And this is done here with Malte, with Arne. And Arne is working on single droplet experiments. And he looks very closely at these experiments here. And so we're looking into these explosions and see what these precursors are actually doing, if they are set free at the same time or not. And Arne here is doing right this. And what he has developed is a method to actually listen to the droplets when they explode and also look at them. So what you see here is a flame around the droplet. The droplet is in the middle. And at some point, the droplet explodes. It's exactly now. And then he listens to it, and with a microphone. And with this, we have a very high resolution, because the image analysis, high speed, is even too slow for us sometimes. But with the droplet acoustics, we can actually look into the droplet explosions much better. And I believe in general on particle technology, we should, and in spray technology and so on, we should do much more with acoustics, because acoustics frequency of measurement is very high, and you get a lot of information out of this. So basically, we have here the acoustic of the droplet ignition. So really, when the droplet ignites, catches the flame, and then here we see the droplet explosion, and then we can zoom into this explosion events, and we have the breakup here. And basically, this gradient is a measure on how fast, how violent this explosion is. And this is what Arne is looking at. It looks at the violence of the explosion and try to characterize and try to categorize explosion events. And you see that looks different here and here, and you also see different signals. And he's been pretty successful in looking at these events and basically categorize these explosion events. And he could trace that back to the concentration you have in the droplet. And once we know that, we can, so this is one of these setups he's using, we can actually looking even closer into these droplets. And then what we see actually, and you saw it here in the video, that there's a vapor bubble forming, and this vapor bubble is growing. And this is because the surface gets blocked of these droplets, and there's no more evaporation. And then the droplet heats up internally and starts boiling. And that's what leads to these droplet explosions. But the question is that important for our materials or not? And this is what Jan can answer here in his experiment. So Jan has a similar single droplet reactor, and now he's from down upwards, or he like his droplets falling down. But he had one very specific setup where you have a camera, and with this camera you can actually look at the spectroscopic lines of these different metals. And with this, he can have a look on which metal is actually coming out of the single droplet. And as we expect, we might really want both metals coming out at the same time when we make lithium titanate, for example, because we need to atomically mix them. So he does this in this interesting looking setup. And he has this spectrometer. And what he is actually doing, he has a small gate width, so we're only looking at certain bands of the spectrum. But then he has a time shift. So he basically, different parts of the sensors are written at different times, and then he can read this out. And what he gets as a signal from this is something like this, and I'll show you right through. So basically, here's the burning droplet coming, and this is a long exposure picture. And then the spectrometer can actually take from each of those moments these kinds of lines. And these are the lines for copper, these are the lines for iron. So this droplet contains iron and copper. And the precursor here is basically for iron and copper almost the same. And no surprise, they come out together at the moment, or almost at the moment of the explosion. There are other species in the flame. This is some combustion products, which we also see. And these species, of course, are there throughout the whole burning. But the metals actually come out only at that moment. If we do that a different way, we change the precursors. We use a copper naphthenate and some iron that evaporates fast. Then, of course, we see, not of course, we figure this out through some really tidy experiments. The iron comes out first and is already in the gas phase. And then the copper only comes with the actually explosion. So we would not expect that these particles are so atomically homogeneous. And I'll show you that in a second. So basically, to make that story is we have these two different precursor solutions. And at this one here, copper and iron come out at the same time. And at that moment, that is the droplet diameter. And the deviation of the droplet diameter is the burning constant. At that moment, the burning constant goes down because evaporation basically stopped. Then we have the explosion and everything comes out. While in the other case, the iron comes out first and the copper later. And you also see a difference in this burning constant, although you have another explosion here for the copper. All right. So Jan was able to collect in single droplet experiments. So you really have to imagine these are droplets smaller than 100 micron. And then each droplet comes out, and then you need to collect the particles from these very tiny droplets. So it took him a while. So he was successful and he listens to some music too. And he was successful in actually collecting some of these powders. And he did the analysis in the high resolution TM. And here you see iron and copper is always together in the case where both of them come out at the same time with the explosion. While naphthanates of copper and iron evaporate differently in the single droplet, you get more iron containing particles and more, these are the iron containing particles, and more copper containing particles. So basically they look more separate. And this gives us a very clear design principles. I think I have some better pictures even here, some more magnification. So these are really like mixed in within one particle, while these are not really mixed in one particle. So to make my story, if you really want to have this lithium titanate and you want to have phase pure, you need to make sure things come out at the same time. And this, you need to make sure you understand this precursor chemistry and this whole explosion events. And if these happen, we now know that you actually can get very phase pure and well mixed, atomically mixed multi-component metal oxides. Okay, of course, we also look at the price. And actually what we had checked also is one of the lowest prices for one of the most phase pure materials that we are very happy. So you also can adjust at the price and how you choose your precursors. Of course, we also tested these for if they're really battery type of materials. This is a study done with Fraunhofer EFAM here in Bremen. And then we made pouch cells from these. So the anode is the lithium titanate. And we made those battery cells. And we tested it at different C rates for these different precursor combinations for the ones that are phase pure. But they're not all the same. They look all the same almost, but there are really subtle differences, not so much in the specific discharge capacity, which is really, really good. It's almost 100% the theoretical capacity. But in the high C rates, we clearly see a difference between our different precursor combinations. So actually we can trace back what we used as a precursor towards what we see in the battery, and the best performing ones are actually those. And the question is, why are not these are so well performing? And then we couldn't see it on the powder. Powder looked the same crystallographic, highly crystalline, same size. But there was a little bit here with the thermogrammetric analysis. There was a little bit of some combustion products we have sometimes in this process, little bit left compared to the green ones. And this little bit already were shown here. So basically, either you know what you're doing, or you need to pre-treat your powder to really get rid of everything that has been basically absorbed on the surface, and then put it in a battery. But you can also just have a treatment step where you treat them to get surface pure materials. Okay, so I have a few minutes left. And so what we did here in this case, we basically had the carbon coating and everything done with the doctor plating. We used our particles, and then we had those flames. So we're saying, why not just make the carbon with the flame together and then maybe have everything in one step? And we also can do this. So this is a carbon flame. It's an exaggerated picture, but it makes the point. I think basically can make the carbon and the actual lithium titanate together, and we mix it. We collect it on that filter, and then we can use that powder directly as a lithium titanate carbon mixture. And schematically, how we do this is shown here. We have these two flames, the carbon flame and the anode material flame, and we collect them on the filter. And then we make one more step, which is also fascinating for me, is we call it lamination. Okay, so we take that filter here with the particle layer on top of it, and we can make that layer any size we want. And we put it on our metal current collector, and we laminate this particle film directly on the metal current collector. So there's no liquids involved. This is all dry. So out of the flame, everything is dry. And then we take this dry powder with the filter and on a dry base, laminate this on this metal current collector. You could think about even roll-to-roll applications on this. And that really is a difference from all this calendering and doctor plating and drying and so on. And it's a one-step process. And if you make things right, these actually work quite nicely. As you see, like we did for the same material, we did lamination and doctor plating. There's not so much difference. We even got some better results for high C rates with our laminated products. That's a bit hard to explain why, and I really cannot, but it shows that the process is working. So maybe you have an explanation and tell me. But I think it's convincing that this one-step process is working for us. And since I come back to this, since we have this porous layer, which is basically on a flexible filter, you can also make this on a flexible metal current collector. And so we are thinking maybe these electrodes that are part of a battery are even flexible. So we did exactly this. So we deposit our particles in a dry form. So they don't need to be dry, they don't need to be sintered, nothing. On the electrodes, we made a little cell out of this. Again, this is collaboration with Fraunhofer IFAM here in Bremen. And then we start bending because we thought that this is flexible. And while we bend up and down, here we see that we have some drop in the capacity, but basically it's not breaking. These layers hold and stay intact. And this is because of the porosity and the interlocking of these aggregates we make from the flame, which I find quite fascinating. So I hope I gave you some flavor. I stick here to the battery performance, but I think you could believe me also that we can make this for other applications. So in the end, to bring some take-home messages. So for us, for our process, precursor solvent combinations are key to select them. Sometimes, and we have a whole program on this, it's written here is heteroaggregation. Sometimes you want them actually separate. You want particle A and B work together in a little symphony to make new properties. But sometimes you want material A and B in one atomic crystal together, and you should decide. We can do both, and I showed you how we make them in one crystal. In my last talk, I showed you how we make these heteroaggregates. They are highly crystalline, and that's very important. We have a dry process. So in some way, yes, we combust a lot, but we don't have any cleaning, any solvents, any use of this. And we can even make this whole deposition. We can add some other components like carbon or other materials right into it. We can basically mix these things at a nanoscale. And I think I could convince you a little bit that we have a method for doing that for batteries. In interest of time, I think I'm almost at the end to say thank you. I give you this almost like New Year's Eve, right? And we almost have that. Thank you for your time here with us. And that is, thank you to the people who actually, or to the agencies who have supported our work. And I'm looking forward to your question, and I hope I see you all at PARTEC in September, and then we can have some more discussion there.
Thank you very much, Mr. Mädler. So you are now free to ask your questions into the F&A button at the bottom of your screen, and then I will forward the questions to Mr. Mädler. So we will wait a few seconds that you can type in your questions. So we have one first question. So first question, for which other materials or application can this flame spray methods be used?
Yeah, I expected that question because I said catalyst sensors and batteries here on this slide. So it's I made this point here because I only have 20 minutes for batteries, but you can also use this for catalysts. So we can really make multi-component catalysts, even with noble metals. And also in sense of multi-component, we have cobalt catalysts supported on alumina, silica, titania, or mixtures of those, especially for CO2 conversion. So that's a topic I'm working right now together also with University of Ulm. And also sensors is a word here. So gas sensors. Gas sensors are electrochemical sensors that work basically on if you have a gas and it reacts on that material, it changes the electron density, and you can actually measure that electron density if you put a current through the particles and have two electrodes to put a current through these two particles. And the really nice thing about the sensors is that we deposit our active sensing layer directly on the interdigital electrode of those sensors. So there's no more step in between. It's all dry. We just spray that on these sensors and then they are done. It's quite nice for these applications.
Thank you for answering. So I check the F&A button. One other question. Can you metal oxides be made or also other materials?
Yeah, maybe I go here. So as I said, this is a picture by Malte. Malte did his PhD with Udo Fritsching here from Bremen. And this is basically in a flame that runs with oxygen. And anytime you have oxygen and you have a metal component here, you most of the time made metal oxides. But recently we were able to actually show that we can also make sulfides. And sulfides can be made in two ways. You can either have, instead of the oxygen, you can have some kind of sulfur source in the gas phase. We're working here on H2S. And the other way is to put the sulfur source directly into the liquid. And then you have to make sure that you still have enough oxygen to drive the combustion, but you have not enough to get oxides, but you have enough sulfur to get sulfides. And here we actually, this is just a breakthrough the last couple of years, to have really nanocrystalline sulfides. And I think what is super important with sulfides for our process that we can make also multi-metal sulfides. The same thing you have seen with oxides, that you have one crystal and you have many metals inside. This is also possible with the sulfides. And actually, this is not so easy with other processes to have them really atomically mixed with a high surface area in terms of nanoparticles. So these are the new developments. Yeah, great question.
Okay, perfect. One another question is about the F&A button. So how rough or smooth is the surface of the deposited particles after the flame spraying? Could it be used as an alternative to sputtering in the future?
Yes, it is. It is actually quite flat. And we have two methods of depositing this. I showed you let me just check I think it's somewhere here. Right, so I showed you taking the lamination process. What you can also do, you can for the sensors, we can directly put the sensor here and deposit directly on the sensor. For this, we actually use a temperature gradient. We call the process is thermophoresis, and then the particles driven towards the cold surface of the sensor, and we deposit directly here. These are super smooth surfaces. However, they are porous. Okay, they are porous in the sense that for direct deposition, they're 90% porous, so highly porous, which is super for gas sensors. While in the lamination process, you can actually change the porosity with the pressure you apply. So you can change the porosity a little bit. Here, the smoothness is determined by the smoothness of the actual filter. So if you have a filter that has a lot of fibers and sticking out, that will be impregnated as a profile also on your surface. So it's not completely smooth. So if you want to have something super smooth, we should check on how we get the layer on top. But for direct deposition, super smooth, highly porous. For this one, porosity can be changed, but you have the roughness of the filter. I hope that answers the question.
Perfect. Thank you very much. We have another questions directly to me over the chat function. So if you don't understand the questions, I can hand over it to you per chat, but I think you will understand it per talk. So in the acoustics spectra, one could see some smaller peaks before the actual explosion. Do you know what those are?
All right. Maybe not, but maybe I can find out with you. Here, these ripples, we don't know. We didn't look at them. I mean, this is clear. This is really where the ignition happens, where it's not where we actually set the spark. The spark is much earlier, but where the actual flame established. Okay, so this is the biggest peak here. And then, yeah, there are some ripples. That is hard. I actually, let me see if I can call this up here. So you maybe mean this. No, we haven't looked at them yet. We were only looking at this. But whoever it is, if you have an idea, let me know. We can look at it more closely. We were first concerned to this peak, which we think is its derivative. The derivative of this peak is a strength of the explosion. And but we have not really looked at the ripples before. But let me know if you have some ideas.
Perfect. So then I think we could ask every question who's coming in. So thank you again very much, Mr. Lutz Mädler. And I will now hand over to Professor Dr. Nicolas Vogel with his topic supraparticulate powders with emergent functionalities. So Mr. Vogel, the stage is yours.
Yeah, thank you very much. I'm currently sharing my screen. And I'm not sure if you can see it. Probably the wrong way around, right?
Yes.
Okay, 1 second. Okay, so now I can change it. Perfect. Yeah, thank you very much for this introduction. What I want to talk to you about a little bit is superparticles and what those are and why we think those are interesting. So to a certain extent, this complements what Lutz has talked about quite nicely, because in our case, everything will be wet. We typically come from dispersion, so particles in aqueous typically solutions, and not from flames. But I still want to show you what we can do with such defined particles. So in a nutshell, if you want to tune out, that is kind of what I want to convince you about. We take small particles and we make them into larger particles, and out comes something that is more than just the sum of its parts. And why that is, I just want to go through with you a little bit. So we all know that there is a lot of particles in this world, anything from coffee to catalysts, as we've seen, battery materials and mundane objects. But very often these powders can be fairly ill-defined. So here's just a random example of a powder that is used for additive manufacturing, for powder-based 3D printing. And you see that this is kind of irregular in shape. So the question is, what happens if we make these powders more defined? And this is what we propose. Those are superparticles, and the definition of such a superparticle is simply, if you want, an agglomerate. So a particle made from a smaller part, made from smaller particles. But in our case, we try to control the shape and the structure and the dispersity of these superparticles as well. So why is that useful? Because in a superparticle, you have a lot of degrees of freedom on how to tailor the properties. So for example, you can change the primary particle sizes, which you see gives rise to different internal properties. If we use polymers, we can play with sintering to either strengthen the mechanical properties or also to tailor roughness and porosity and so on. Then we can influence the composition, so we can mix different primary particles, and that gives us then, of course, a mixed superparticle. And via changing size ratios, we can even control where these individual particles are in such a superparticle. So smaller particles, especially in fast processes, tend to accumulate on the outside of such a particle. But then finally, we can just combine these things, so we can add more mixtures to make more complex particles. We can then melt some of the particles to tailor them together while others will persist and so on. So it's quite a big playground on how to tailor composition, structure, and properties at the end of the day. How do we make superparticles? In our lab, at least, we have, in a sense, two technologies. One is droplet-based microfluidics that you see here on the left-hand side. So what you see here is a stream of a water-based dispersion of particles, and here you have an oil stream. And at this intersection here, they are split up, the continuous stream, and we have these very uniform droplets of particles. And this is, of course, very useful if you want to make defined particles and study structure property relationships in great detail, but it doesn't really come out in huge quantities, so it's not so easy to make macroscopic materials from this. And here on the other side of the world, you have spray drying, which I'm sure all of you know is just a very bulk or very large volume type of processing. So what you do is you evaporate a dispersion here at the nozzle, you vaporize it, and then it dries out, you collect it here, and then you create particles that actually do not look fairly different from the microfluidics, but in the distribution of particle sizes that you obtain, of course, there's big differences. And because the time scale that you need for consolidations are very different, there's also some different physics at play that we can either leverage to our advantage or that we need to overcome in terms of ordering and so on. Okay, good. So now I want to run you through a couple of examples on how we actually use these superparticles. And the first thing I want to talk to you about is how we can tune porosity in these particles. So why do we want to create porosity? There is, of course, different applications. One is chromatography. That's something that we are currently developing in a collaborative research center. And what the goal here is we make a porous material. You can also play with the surface chemistry. And we want to use this to sort smaller particles according to their size or shape or maybe even surface properties. And if we want to separate particles, of course, the pore sizes need to be matched to be somewhat commensurate with the size or the average size of the particles that we want to separate. And the second aspect is catalyst support. So whenever you have a heterogeneous catalyst, these particles need to sit somewhere. And you typically do this in a porous medium simply because you have a high surface area. And in this case, it's important to also consider that you want to have larger pores to enable efficient transport. Okay, so how do superparticles come into play here? So if you again look at the fabrication process, you see we have the particles here in an aqueous dispersion, and as it dries out, it eventually consolidates. And here you can already see that by changing the primary particle size, we can create different porosity simply because that is inherited by the interstitial sites of this colloidal packing. So this is what you see here, but we can also leverage different types of pores. We can make smaller pores simply by using porous primary particles, zeolites, mesoporous silica, metal organic frameworks, and these type of things. And we can introduce larger pores by introducing polymeric particles that we can then either dissolve or burn away. Or we combine all of these to make a hierarchical material. Here's just some examples to show this. So here you see a simple spray-dried superparticles made from fairly uniform silica primary particles. And what you can then see here, if we change the size of the primary particles, the pore diameter becomes larger. It's not very surprising, it's simply because there's bigger holes in that packing. But what is surprising to a certain extent is that even in this very fast spray drying process, the average pore size that we measure in our system is very close to what we calculate for an ideal sphere packing. And that means that even though you have a very kinetically controlled process, the ordering in our material, which you can kind of see here as well, is actually fairly well. So the pore size is reflected by that we would have for the densest packing of spheres. But then we can add mesoporous primary particles to make superparticles. They will look essentially the same. But if we zoom in, we can see the mesopores in the primary particles. And of course, if we then measure the pore size distribution, we see that we have smaller pores from the primary particles and the larger pores from the interstitial particles. Well, and then we can also add larger macroscopic particles. Here's just an example where we add a few larger polystyrene particles. You see how they penetrate here. If they're larger, they accumulate more in the inside. And what you see here before calcination, we only have that pore size distribution coming from the interstitial sites. And upon calcination, we can then introduce a larger peak that could be used for transport pores and so on. Now we can also change this, and depending on how big we make our polystyrene particles, we can then control that larger pore dimensions as well. Good. So why bother? Here's an example about SCALM's catalysis, which stands for Supported Catalytically Active Liquid Metal Solutions. So it's a new type of catalyst that's being developed here at our university, and that, in a sense, uses a particle droplet. So it's formed from a liquid metal solution, typically gallium, where you dissolve active species. And these active molecular or atomic species, platinum, palladium, and so on, they act as single catalysis, and because of the dynamic nature, they can disappear, come to the interface and disappear again, and that changes, in a sense, the catalytic conditions, reduces coking, creates higher selectivity, and so on and so forth. So it's a fairly attractive system that a lot of people, at least here in Erlangen, are currently playing around with, but there is a key difference to normal heterogeneous catalysis. And that is that the particle size of such systems is much larger than what catalyst people are typically used to. And this is what you see here. The way this is prepared is often by ultrasonication or by comminution. And what comes out is something around 100 nanometers in particle size. And that means that any conventional catalyst support simply has pores that are way too small to accommodate the particles. And then we came up with this idea of using our superparticles. So this is what you see here. This is a typical catalyst support, and you see all the catalytically active particles reside on the surface. And since they turn metal under liquid under reaction conditions, they will start to coalesce and then lose surface area, and by this, activity. And in contrast, in our superparticles, you can hardly see stuff, but you see these small particles that sit in the interstitial sites at the surface, and that means that they are trapped. And that means that they cannot move on the surface and do not coalesce, and that then increases the overall stability over time. And that's exactly what we see here for just an example of propane dehydrogenation. And what you see here is that productivity of the particles firstly depends on the amount of material that gives the overall height here, but more importantly, the gradient, so how quickly it runs into a steady state and whether or not it decreases or not, is very different from our superparticles, which is these colors here at the bottom, as compared to conventional catalyst supports. And that shows you that really we trap the particles in their native state and then can create a higher long-term stability. And here's a second example. This is about adsorption. Metal organic frameworks are very important materials for gas adsorption because they have very, very large surface areas. But the problem is that when you use these in a bulk, the pores are very poorly accessible because gas needs to squeeze into this framework over large spacings. And the question here was that whether we can introduce a hierarchical design to reduce mass transport limitations. So in a sense, make metal organic framework primary particles, put them into a superparticle, stack the superparticles into a pellet, and then assess how this hierarchical pore structure affects the transport. This is how such a particle looks like. So you see we are able, or our collaborators, Professor Watanabe from Japan, are able to do these particles very precisely. And if we now look at the gas absorption properties, we see that we have different pore sizes. So we have the interstitial sites of the primary particles, and we have these very large pores that relate to the packing of the superparticles. And when we now look at the kinetics of the absorption, what you see here in blue is a normal powder of such a metal organic framework. And you see it takes quite a long time until we saturate the pores and absorb all the gas. And in contrast, a pellet made from superparticles, because now this is much more porous and has these large transport pores, can be charged really, really quickly by a factor of approximately 30 difference. Okay, so in the next example, I want to briefly talk about 3D printing. And in the case, what we are using is selective laser sintering, where we use a powder bed and then a laser that heats up a polymeric material and fabricates such materials within this powder bed. And without going into details about the material selection, I just want to highlight what is very interesting and appealing in superparticles. And that is we can in situ tailor the roughness of the particles, which we can use to lower the adhesion of a powder. Why? Because two smooth spheres can come fairly close together and then start to interact via van der Waals adhesion. If we have a rough sphere, then these small roughness features prevents direct contact, and that means the particles are further apart, and that reduces the attraction. Now you can calculate the adhesive force, and you see that this will be lower then. And that was kind of what we set out to do. And this is just a very simple example of PMMA particles. We are now doing this with biodegradable polymers and so on. But the concept is always the same. If we compare smooth particles to rough superparticles with different primary particle sizes, then you see we can make powders that essentially look the same, except for the surface roughness is a bit different. And when we now look at how these powders flow, which we assess via a tensile strength, then you see the introduction of surface roughness really, really drastically changes the tensile strength or the cohesion within the powder. And as a result, if we compare the flowability by simply doctor plating a powder layer, you see that the superparticles flow very well and form dense layers, while the same particles with a smooth surface do actually not flow so well and then create problems in your powder bed. And that will translate, of course, to the final printed product. And as the last example that I want to introduce to you is an example that I picked from nature, and those are structural color pigments. So if you now close your eyes and imagine your favorite animal, it's not unlikely that this animal has very beautiful colors. Here's an example of a butterfly. We all know how beautiful they can look like. And if you zoom into these wings here, then you see the colorful scales. And these scales have a very defined nanostructure. And that is responsible to create these optical effects by interference with light. So in this case, also the hierarchy is important, in particular this nanostructure. And when we cut open one of our superparticles, if we make this from primary particles, we see that we, in a sense, have a very similar structure than the butterfly wing, because we have very ordered layers here, and we can make them in the same size range as the butterfly. And that will lead to structural coloration by the same interference effect that we observe in the butterfly. And in a sense, if we sum this up a little bit, there is multiple optical effects in such superparticles that can take part at the same time. The first is what we typically want is a Bragg type reflection, so that light is reflected by all these individual layers and then comes out, depending on the size of the layer, in a certain wavelength that's being constructively interfered. But we can also observe grating diffraction effects, so an effect from the surface. And if we don't have perfectly ordered superparticles, we always have scattering by incoherent scattering, so white light, by defects and irregularities, which are typically found in the middle of the structure. So how can we now leverage these things to actually make structural color pigments? The first thing is we can change the size of the particles. By this, change the interference for constructive the conditions for constructive interference. And this allows us to make structurally colored materials all the way through the visible spectrum. So from blue via green to red, and if we want, we could also make them smaller or bigger or in between. So this shows us that we can really not only mimic the colors in nature, but tune the colors the way we like. But we can also leverage grating diffraction effects if we make the size of the particles larger. And then you see that instead of a single color, we start to see this rainbow-like interference effect on the surface of the particles. And that's a telltale sign of grating diffraction that is manifested in superparticles with larger primary particles. Well, and finally, scattering is always a problem in structural coloration. And the typical way to mitigate this is the incorporation of absorbing materials. In nature, this is melanin, so all animals that have structural color typically combine this with either a layer of melanin, so our natural pigment, which is either underneath the photonic structure or when the photonic structure is formed directly by melanin particles. And in our case, we can either use synthetic melanin, polydopamine, or we can add carbon black to simply remove the stray light. So why does this work, or how does this work? We have a certain reflection peak from the photonic stop band. This is what we actually want to observe. But because of this incoherent scattering, we also create a reflected light throughout the visible range. And this gives a whitish overall hue to this entire color pigment. And now if we add something that absorbs, typically broadband, so takes out all the light, and we combine this, then we can reduce the overall reflection of light. And at first that would seem counterintuitive because we want to have reflection, but our eyes are very sensitive to differences in reflection. So it pays off to make a crisp color, to remove overall light so that we don't get any reflected light in regions that are not within the photonic stop band, so that the only light that reaches our eyes is the region of interest that we can tune via the photonic stop band of the material. Well, and this is how it looks like. Here is the structurally color pigment, in this case tailored to be blue. And you see, if we only make our silica particles, the color looks white. So the powder, we don't observe a visible structural coloration. And as we add more absorber, you see that this color is recovered better and better. And if we look at the reflectance spectra of such materials, we see exactly what I discussed before. If we have too much scattering, then we don't see any light, so the entire spectrum reflects and it creates a whitish appearance. And as we add carbon black, we see that we suppress the scattering more and more, and as a result, the photonic stopband starts to dominate the spectral properties more and more. And now we can convert these spectra into chroma values, so in a sense, in something that we can measure as with our human eyes perceive color. And then you see what you intuitively feel from these pictures here as well, that with increasing carbon black content, the chroma increases. If we add more and more, eventually it decreases again because we create a black powder. And now we can also play around with the size of the primary particles, and this allows us to make structurally color pigment throughout the entire visible range. So you see the color macroscopically, you see it even better, and you can analyze it much more conveniently under a microscope, and we can measure the spectra that really corroborates with the photonic stopband on the macroscopic color that we see. And with this, I'm at the end of my talk, and as a conclusion, I just want to say that superparticles are more than just the sum of its parts, and they can be used to really tailor the design of properties. We can create a better understanding of self-assembly and structure formation in confinement, but we can create either a higher functionality, as in the case of powder flowability, but we can also incorporate entirely novel properties which are called emergent properties, such as the structural color that I showed you towards the end of my talk. And with this, I want to thank all the people that actually do the work. This is my group here in front of our institute, and then the people that support me to do our research. And this is in particular our CSC 1411, design of particulate products, where we develop a lot of these superparticle systems, but also a range of different actors, generally the DFG, the Deutsche Forschungsgemeinschaft, but also some other players that supported this work. Thank you very much.
Thank you very much, Mr. Vogel. So now you have the opportunity to ask all your questions to Mr. Vogel via the F&A button at the bottom of your screen. So I will give you again a few minutes that you can type in your question. Okay, we have one first question. So you mentioned structural coloration. How precise do you need to synthesize the involved primary particles?
Yeah, that's a very good question. So typically the way we currently tailor our structural color is by making ordered layers. And if we simplify the system to not make particles but thin films, because then they crystallize easier, then one typically says that you need to have size deviations smaller than 5% to actually form ordered layers, and this gives then rise to this constructive interference. But in a particle, that crystallization is already a bit hindered by the curvature of the element. And that means that the particle can be a bit more forgiving in these size ratios that we can use. So you can accommodate to a certain extent more polydispersity. I currently cannot give you a number because this is something that we are currently investigating and seeing. And the second thing is that structural color not only comes from such constructive interference from complete layers, but one can also make photonic classes, so disordered systems, where the structural color comes from short-range order between these materials. And those can be even more forgiving in terms of the distribution of particle sizes. So overall, it depends to a certain extent. To fundamentally study it, it's good to have them as monodispersed as possible, because then you can deduce structure property relations, but starting from this, you can dilute the system more and more into more polydispersed samples.
Perfect, thank you very much. So I have one question also via the chat button directly to me, so I will speak the question to you. If you do not understand it, I can write it to you. For the flowability, the deposited particles seem rather large, and you had the biggest effects for the smallest particles. Why not using even smaller particles?
Yeah, so if I go back to the slide, So that's the question here. So in a sense, the simple answer is because that student that was the smallest particle size that we could reliably make with the PMMA particles before they became so polydispersed that we couldn't determine the roughness fairly well anymore. If you would go down, I would expect it would be better because the minimum that would be anticipated to make the smallest van der Waals forces would be below 50 nanometers or so. But in effect, this was already by far good enough to create a very well-flowing powder, and then we didn't really need to bother anymore. But it's a very good point. It would become better. That would be my prediction as well for even smaller particles.
Perfect, thank you. So I have one other question. In what quantities can you produce superparticles?
Yeah, that depends what I said in the beginning. If you want to make them very precise and use microfluidics, then in homeopathic quantities, so you create some amount of powder, but it's more in the milligram range. If we use spray drying, then it depends on how big your spray dryer is. It's an inherently very scalable process. And then what we currently do is grams, hundreds of gram scale, so enough for tests of 3D printing and so on. But it's a matter of scaling the entire synthesis process. In this case, I would say the spray drying is not a limiting factor, but the availability of the primary particles.
Perfect. So I think we have time for a last question. So what advantages do your polymer powders have compared to conventional materials in powder-based 3D printing processes?
Yeah, so in this case, if I go back to how we make the superparticles, then typically in normal powders are either formed by comminution, so by grinding particles, or by precipitation. And that means that you typically, sorry, that's not what I wanted to show. It's this one here. So you typically only have a single polymer species. So you would be somewhere here. And whenever you want to incorporate something functional, you then need to mix it physically. And that means that you don't have a very homogeneous distribution of multiple particles. And again, you risk that the flowability is not so well. And in our case, we can really accommodate both additives by mixing them in, or even multiple additives into the material without compromising the overall shape and structure of the powder itself. And that, in my view, is a fairly big advantage. Plus, of course, the powder itself just flows very well, which facilitates the printing process.
Perfect. So then I think we could answer all questions. So thank you again very, very much, Mr. Nikolaus Vogel and also Mr. Lutz Mädler. So then, dear participants, thank also you for joining us at the virtual talk today. And the upcoming dates and topics for our next virtual talks can you find over our website, www.pautec-technofarm.com/events-program, or on our social media platform, LinkedIn. So stay tuned and feel free to joining us next year. And we are also very much looking forward, as Lutz Mädler and also Nikolaus Vogel said, for PARTEC 2025 and also PAUTEC Technofarm and Fachpack 2025 from the 23 to 25 September next year. So if you want to take part at PAUTEC 2025, you are very welcome to read through all our call for papers and our new website at www.partec.info and submit your abstracts by January 10 in 2025. So have a nice day and hope to see you soon.